Yes. Yes, I can see that. We have 2 minutes more. How's situation in Mumbai now, Professor Madhu? Hello?
Yeah, there are quite a few cases, not particularly good. But,
the campus is closed now.
At least the institute is functional to a large extent. Yeah,
that's good at least. Oh, how about the research scholars? Are they around or?
Yeah, they are coming in actually. They are coming in.
Okay.
Yeah, Sunil, we can go ahead, right?
Yeah.
It's just a second.
So,
I think I lost my screen here.
Probably we can see the screen, in fact.
You can see it, but I can't see it. That's the problem. Just give me a second. I'm sorry.
Yeah.
Okay, it's okay. We have enough time.
I'm more used to the Zoom thing, actually.
Okay.
But somehow we are not.
Sure.
Zoom
Now you
is
can
so
see it.
simple. Yeah.
You can see the screen right now, right?
Yes,
Yeah.
yes.
So, can we start now?
Yes, yeah.
Yeah. So, good afternoon, all. Good afternoon, Professor Bk Madhu. So, we are starting with our second session of webinar on NMR. I am very happy to introduce and welcome Professor Bk Madhu to this webinar. I know Professor Bk Madhu personally for the last 17 years. After his studies, he joined as a faculty at TIFR Mumbai in 2003. I was a frequent visitor to TIFR NMR facility during that time. Professor Bk Madhu supported me throughout my career. So, Professor Bk Madhu obtained his PhD from IIC Bangalore. After his degree, he did postdoctoral research in Weizmann Institute of Science, Israel, and Johannes Kepler University, Austria. He was a visiting fellow in Stockholm University, Sweden, University of Southampton, UK. In the year 2003, Professor Bk Madhu joined TIFR, Mumbai, as a faculty member. And in 2014, he moved to TIFR Hyderabad campus as a full professor. Professor Bk Madhu is a world-renowned NMR expert, particularly in solid-state NMR. He is the member of many national and international bodies of NMR, like International Society of Magnetic Resonance. He is the editorial member of many NMR journals. Professor Bk Madhu is a visiting faculty in many foreign universities, like University of Leipzig, Germany, Weizmann Institute, Israel, etc. Professor Bk Madhu guided many doctoral students and postdoctoral fellows. He has several hundreds of journal publications, and he is a speaker in many NMR conferences. I heartily welcome Professor Bk Madhu for talking about the basics of NMR spectroscopy.
Thanks to Kumar and Tarunan for the kind invitation and for the generous introduction. I think I have a problem here in this. Can you see the full screen or you just see the...
Not the full screen.
Slide. Yeah, and it's not changing as well. So let me start.
Can you make it full screen? You know, F5 or something.
Yeah, that I know, but it's not coming up actually.
No, but the left corner, you can see that, from beginning, you can slideshow.
No,
Left it top.
that I know, but it's not coming in this.
Oh, right. Okay.
So let me just try once.
Yeah.
Okay, now it should be fine.
Yeah, now it is full screen. Thank you.
Right. Right, just a second. Okay. All right. So thanks very much for the kind invitation and the introduction as well. So I guess there are some people who have joined, and I can start. So I will talk mainly about the principles of Nmr spectroscopy. And I think there was a talk by Chari in the morning, and I guess he probably talked more about the biomolecular NMR. So I will just step back a little bit and introduce to you the principles and the practice of NMR in a rather simplistic sense. So the whole idea of my talk would be somewhat based upon this quotation from Purcell, who was one of the inventors of NMR. And once you invent a nice technique and get the Nobel Prize, you can come up with these kind of romantic statements, which is what he said, looking at the snow. That is nothing but you can imagine them as just as a protons processing in the Earth's magnetic field. And if you actually look at the snow, which is processing in the magnetic field, it's not quite because of the Earth's magnetic field. It's actually because of the dipole-dipole coupling between the water molecules. So that's something which one has to keep in mind. But this is the spirit in which the concepts have been developed. And the development has been going on since the 40s when NMR was first discovered by Bloch and Purcell. And a series of discoveries came in after that. And it's still going on in terms of the methods, in terms of the hardware, some of which we will see as we go on. So I have just listed a few of these methods over here. And we will not talk about all of these things. We will just talk a little bit about the basics of the nuclear magnetic resonance and some of the recent developments as well. So that is NMR in a nutshell. It encompasses quite a large number of areas, right, from physics, chemistry. It started off as a playground of the physicist. Later, it became a favorite technique of the chemist. And then the biologists took over quite a bit. And it is still finding lots of applications in medicine, in magnetic resonance imaging. So it's a very versatile technique in that sense, covering a whole range of science. So what are the potentials of NMR? So it's useful from a very fundamental point of view to understand quantum mechanics of the nuclear spin system. But that's something which we call as a spin choreography. So how to essentially manipulate the spins and get the maximum information. And we will see some of it as we go on. And that is the process with which we can characterize several of these materials, study the properties and the dynamics of the compounds like biomolecules, proteins, and so on and so forth. And as I said earlier, it plays a pivotal role in producing high quality images of various objects as well as the human body. So that's again a little bit of an elaboration of the potentials of NMR in terms of the structure elucidation. Structure is not the only thing which is important. The strength of NMR essentially, in my opinion, is in studying the dynamics. There are various other methods to look at the structure. NMR has its niche areas, but the main thing of NMR, which X-ray or EM fail in a large respect, is the dynamic processes. And that's something which one has to keep in mind as the basic forte of nuclear magnetic resonance. And you can look at the functional properties of the macromolecules, design of drugs, for instance. Once you know the dynamics and the structure, NMR is a good tool to design the drug molecules to target a particular protein and prevent the deleterious functioning. And of course, in medicine, it plays a role in magnetic resonance imaging, also in the analysis of a large number of metabolites. So again, it has applications over a big range of the science field, and of late has been playing a pivotal role in understanding the disease-causing proteins such as the prions, HIV, the Alzheimer's, and so on and so forth. In metabolomics, it has created a huge platform of the data analysis the data collection, the analysis, and the statistical methods to understand what are the kind of metabolites which could be responsible for not just the disease, but even for the onset of the disease. And that knowledge is quite interesting to have a profile of patients around the world to design the drugs and to understand the processes of setting in of various kinds of diseases. So that's again an important aspect. And that's a slide which sort of tells you how the MRI plays a key role in essentially mapping almost every aspect of the human body, from the ligaments to the brain to the tumors to lungs, everywhere actually. So it's a versatile technique in that sense. So what is nuclear magnetic resonance? So as most of you might know, it has 3 letters over there, the nuclear, and that refers to the nucleus of the material. And what we are probing is the spins inside the nucleus, the spins of the neutrons. So that's the essential probe that we are using to get the structures, and how the spins actually can be used and manipulated is something which we have to understand as we go on. The nuclear spins by themselves cannot give you any information, because as you see over here, left to themselves, they are just oriented in a very random way. So there is no net magnetization which is coming from the nuclear spins. So the spin is one of the most complex objects to define. It suffices for our understanding to treat it as a magnetic moment, or just like a bar magnet. And the only difference here is spin is an intrinsic property. It's not like a mechanical property. So even at an absolute 0 temperature, you still have a spin, and the spin, or by the spin angular momentum. The orbital angular momentum will cease to 0, but the spin angular momentum still exists. And that is a random orientation if you have nothing to align. So what a magnetic field does is to give preferential alignment to the whole class of spins. Some of the spins point in the direction of the magnetic field. Some of the spins will point against the direction of the magnetic field. So I have plotted here 2 levels here, and that's assuming that you have one spin half. A spin half in a magnetic field will split into 2 levels, and each level will have a population. The difference in the population is the one which gives rise to the NMR signal. And how do you actually create a population difference is by the magnetic field. And how do you induce a transition is where the resonance comes in. So the resonance is a phenomenon in which you have to talk to these spins, talk to these populations, such that there is a transition between this level and this level. And that is the process of the resonance. So you have to come up with some perturbation, which is of the order of magnitude of the energy difference between these 2 levels. And that energy difference is of the order of, in the radio frequency regime, of the order of megahertz. And that's why you apply the radio frequency fields to excite the transitions, or to create a transition between these 2 levels. And that is a transition which we can record, and that will have a unique inherent signature of the environment of the spins and the interaction of the spins with other spins in the sample through the through-bond coupling, the space coupling, and so on and so forth. So that's the essential idea that we are going to talk about. The nuclear spins, as I mentioned earlier, is a fundamental property, just like the charge and the mass. And if you look at the deuterium atom, which has got a proton and a neutron in the nucleus, and that's the blue one is a proton, there is a red neutron, and the electron is just moving around the nucleus. The electronic spin here is half. The nuclear spin here is 1, because there are 2 spins, spin half, They add up in a constructive way, and you get a nuclear spin of half. So that is an active NMR nucleus. So you can probe the properties of it. But if the nuclear spins are paired, then they are useless in the sense that they don't have any particular spin. So like if you look at the helium atom, so there are 2 protons and 2 neutrons. And as the Pauli's exclusion principle would tell you, they will pair up such that the neutrons will pair up with 1 up and 1 down. The protons will pair up with 1 up and 1 down, and the net spin is 0. So there is no net nuclear spin. So helium-4, the naturally occurring one, is NMR inactive. But helium-3, on the other hand, is NMR active. The carbon-12, which is the most abundant of the carbons, is actually NMR inactive, because there are 6 protons and 6 neutrons, and the spin go to 0. While the carbon-13 has 1 extra spin, and that gives a spin half for the carbon-13. Similarly, for nitrogen-14 is spin 1, nitrogen-15 is spin half, and so on and so forth. So it depends upon the number of protons and the number of neutrons you have in the nucleus, and how you can actually club them together following the Pauli's exclusion principle. So once you understand that, and if you look at the periodic table, now pretty much every element is NMR active. They may be naturally less abundant and so on and so forth, but that's a different aspect. So you have at least about, and the spin half is only a minority. The spin half is just about 25% of the periodic table. The most prominent ones, as you might know, on the one edge, which we call it as a proton, it's the real hydrogen. It's just one proton, so that's why we call it a proton. We have a carbon-13, nitrogen-15, silicon, phosphorus. So these are the common spin half elements. But you do have other elements which are greater than spin half. And deuterium is one such element with spin 1. You have sodium, which is spin 3 half, oxygen, which is 5 half, lanthanum, niobium, potassium, and so on and so forth. There are plenty of such elements. And these are called the quarter pole spins. They're much more difficult in terms of the NMR, but much more useful because these are the elements which come in a variety of industrially important compounds. Oxygen is very abundant, and 14 is another one. So there's a whole lot of spectroscopic development which is going on in the field of looking at the quarter pole elements. Sunil, so the presentation is going fine, right? The talk is audible and the slides are visible, right?
Yes.
But yeah, it is visible. It is visible. Yeah.
So that's about
yeah.
So that's about the distribution of the elements in the periodic table. So pretty much everything, as I said, is NMR active. Many of them may be naturally less abundant, and many of them have a very low gyromagnetic ratio. So what is gyromagnetic ratio? It's said that spin can be as constant containing a charge spin at
It's not. There's some problem, I guess.
right.
Voice is breaking.
Okay. How's it now?
Yeah, it's good.
Okay now.
So once you have the magnet, you can think of as a magnetic moment. That is this guy, the mu. The magnetic moment, the spin part. The spin part was 3 half or 5 half. Okay. The proportionality constant is this gyromagnetic ratio and the Planck's constant. The Planck's constant is a constant, but the gyromagnetic ratio is on a particular nuclear spin. Sunil, I think some of the audience of their mic form, I believe. I get this. So maybe can everyone switch off the mic? Yeah, I think it's
Voice is breaking actually. It's not continuous. Something is.
right. There's nothing I can do, unfortunately. Let me see.
So mic is very close by, or?
Yeah, no, that should work. It always works. So there is no particular reason not to work today. How is it going now?
It's not that good.
I see.
Initially, it was very clear.
Initially, it was clear. Okay.
Initially, it was. Your phone is very close.
I can put the microphone. Let me just give me a second. Let me see.
Yeah.
So how is it going right now?
Yeah, it's fantastic. It's
Now it is clear.
All right.
yeah.
So there is a magnetic moment, and the gyromagnetic ratio is the constant here, and that's a constant which is dependent on the particular nuclear spin. And in a physical sense, the gyromagnetic ratio tells you how easy it is to magnetize a given element. So that's the whole idea behind it. So the larger the gyromagnetic ratio, the better the response of NMR from a nuclear spin. So protons have a higher gyromagnetic ratio. Carbons have lower ones, about 1/4 of the protons. Nitrogen's 15 are even lower, like 1/10. So there are two things which one has to consider when you talk about the sensitivity of NMR spectroscopy. One is the natural abundance of the nuclear spins, and one is the magnitude of the gyromagnetic ratio. If both of them are on the higher side, you do well. If they are not, then you have an issue. And that's where people have come up with methodologies to make it better and better. Right. So once you keep the nuclear spins in a magnetic field, as I said earlier, they allow Sunil, can you please ask the audience to mute the mic? There's all kind of vehicle horns and all I'm getting actually.
Yeah, please switch off your microphones, all the audience.
Thanks. Yeah. Right. So the nuclear spins get aligned in the magnetic field, and what they essentially do is that it's a magnetic moment. So it keeps precessing in a magnetic field. And as an analogy, you can think of as a spinning gyroscope in a ship, for instance, in a gravitational field. So that keeps on precessing and tells you the direction in which you are going. And that's the same thing over here. So there is a magnetic field which we say is aligned along the z-axis. It could be x or y, that doesn't matter. But as a convention, this is taken as the z-axis. And then the nuclear spins just keep on precessing about this magnetic field with some particular frequency. And that frequency is what we call as the Larmor frequency, which is of the order of megahertz. And that is of the order of megahertz because the energy difference between the two levels, which I will show you a calculation in a while, is of the order of megahertz. I think there are several people saying that they can't hear. Is that true, Sunil?
The sound is a little bit low, but I think if they can increase the volume of the device, maybe they can hear.
This is the maximum, actually.
Yeah,
No,
the audience can increase the volume of their speaker or something like that.
Yeah, I don't think I can do anything because this is what.
Yeah, it's audible to me.
Okay.
Yeah.
All right, let me just go on. Right, so that's the magnetic dipole moment and the precision frequencies, which are characteristic of each nucleus. And I have given here a list of these, the common nuclei that one looks at along with the spin quantum number. And you can see that there is a big range of the gyromagnetic ratios and the natural abundance as well. If you look at the carbon-13, the receptivity is about 1/4 with respect to the protons. If you fix the proton as 1, the sensitivity is 1/4. But more importantly, the natural abundance is just 1%. That's a very weak number, actually. But that's the fact of life. So again, to sort of recapitulate, you place the nuclear spins in the magnetic field, and you get the Larmor frequency, the precision, which is coming from the splitting of the energy levels in the magnetic field. That's called the Zeeman splitting. If you don't have the magnetic field, you get there is no splitting. The energy levels are degenerate, and as you increase the magnetic field, you get a larger and larger splitting, and the transition also becomes higher and higher. So that's the whole point behind the spins and the magnetic field. And then you come up with radio frequency perturbation that can actually induce the transition between the upper level and the lower level. And that's the transition which you record. So this transition is essentially, it's a fluctuating electric field or the fluctuating magnetic field, which can cause signals. So, it's a charge which is going around. A moving charge will actually cause an oscillating magnetic field, and that is which we actually pick up from this transition difference. And later, what you do with that is a question of detail, but this is the essential physics of creating an energy level separation of a spin in a magnetic field and causing a transition by the application of a radio frequency field. Now, the question arises as to how you can actually, look at these, the spins. So we said that the spins carry the information. Now, the information content is actually provided to the spins by the various interactions which are present in the spin system or in the sample. And these are the chemical shift anisotropy. We will see that a bit later. The dipole-dipole couplings, which are through space, and the through bond, which are the scalar couplings, which of course you will be familiar with in all your chemistry compounds. And as I said earlier, you can have the quadrupole coupling if the spins are greater than half. So that's essentially the different kind of interactions which the spin system provides, and which is something which you can actually take into account. Now, there are different kind of interactions. So the interactions which we deal with you can classify them into an external interactions and an internal one. And the external ones are the Zeeman magnetic field, which is external magnetic field, and the time-dependent radio frequency field. The internal interactions can be your chemical shift, the dipole-dipole couplings, the through bond, and the counterpole couplings. So these are the responses which later add up to the spectral quality.
Dr. Madhu, can I interfere?
Sure.
Many participants say that they can't hear you. Is there anything you can do there?
I can't.
Like, micro, can you keep the mic to very close a little bit?
I'm just doing the way I do every day.
It's audible to me, but some people can't. They said they set to everything 100% and still they can't.
No, then it is their problem.
Yeah.
I can't do anything here. Actually.
Okay. Okay, let's go ahead.
So that's the nuclear spin interactions can be further split up into various aspects. So you have the chemical shift terms, and which is a magnetic interaction, and then you can have a spin coupling, in which comes the scalar couplings or the dipole couplings, and then you have this quadrupole coupling, which is actually an electric interaction. But these are more of a detail, so I will not talk about any of these interactions today, but I will talk a little bit about the chemical shift and the spin couplings, which are the abundant ones as far as the NMR of solution state is concerned. So that is essentially a recap. So you have the nuclear spin, you have the NMR magnet, you have the precision with the Lambda frequency, and the transitions can happen between the lower level and the upper level. And you can get the NMR spectrum. So you get a time-dependent response, which you can take a Fourier analysis and get the NMR spectrum. So that's something which we will see in detail. There's one subtle aspect that one has to remember here. The resonance condition that's the Lambda frequency. The omega, which is the Lambda frequency of the nuclear spin, is proportional to the magnetic field multiplied by the gyromagnetic ratio. And as you can see in your electromagnetic spectrum, the NMR frequencies, which is radio frequency in the order of megahertz, come way below in terms of the energies. So you have much better techniques over here, like the gamma rays, X-rays, which have higher energies, and the radio is much at the lower end of the electromagnetic spectrum. So what's the implication of that? I mean, that means the NMR is actually an extremely low sensitive technique, unlike its electronic brother, which is the EPR, or the optical spectroscopies and X-rays. It's very, very low sensitive. Now, low sensitivity is bad, but the good thing of being low sensitive is the time scales are much longer. And that means that the resolution is pretty good, which means that you can actually have a site-specific information using NMR compared to the optical ones or even the EPR ones. So you have a disadvantage in terms of sensitivity, and that is an advantage in terms of the resolution. And I will sort of give you some numbers of the disadvantage in that sense. So that is what we have talked about so far. You keep the sample in a magnetic field, and you have a good orientation of the nuclear spins, and you apply the radio frequency waves. Once you switch off the radio frequency, the nuclear spins will emit the absorbed radio frequencies, and that's the one which you record, and what we call it as a free induction decay. So this is a time domain signal which you Fourier transform to get the frequency response of a given sample. So that is fine. So let's just let's see a little bit about the hardware that we have. I understand there is another talk tomorrow which will talk more about the hardware, but that's how the hardware has evolved in the NMR. So that's a magnet, that's the probe in which you keep the sample, and that's a schematic of the spectrometer or the electronic consoles. And the magnet has evolved quite a bit over the years. So this was perhaps the first of the magnet which Bloch had in 1949 in Stanford. And later we had the electromagnets, not the superconducting magnets. And then we have, again, the console developed, the electronics developed quite a lot, including the Fourier analysis and so on and so forth. And then came the superconducting magnets. Now you can see that the magnet and the console all come in one unit as long as you go for low field spectrometers. And then you can have very high field spectrometers. So these days, people even have 1.2 gigahertz, which is substantially higher magnetic field, and you can apply a large range of very sophisticated pulse schemes, the ones which I've shown over here. and get complicated spectra of very complex molecules, analyze them, and get the structures. And that has become pretty routine in the case of solution and solid-state NMR. But we will not go into these details. I will still concentrate a little bit on the physics of the NMR. So that's again a plot of the distribution of the spins or the populations in a magnetic field, where the difference, the energy level difference given by the Lambda frequency. So gamma h bar is the omega, the frequency, and that's the B naught, which is the energy difference. So when you don't have the magnetic field, the spins are randomly oriented. When you have the magnetic field, there is a net orientation, which means that there is a net population or a net magnetization. And that's the magnetization which you can manipulate later to get some sensible signal. And that sensible signal is obtained by applying an external perturbation, which is a radio frequency pulse in this particular spectroscopic technique. And that can give rise to a spectrum. In this case, it is a spectrum of ethyl alcohol. I mean, you can get multiple peaks over here. So normally one would expect that all the protons precess at the same Lambda frequency. And that has been found to be not true. The frequency of precision is not the same for every similar element. It actually depends upon the chemical environment. So the CH3 behaves in a different fashion compared to CH2, which is different from the OH protons. So you get three distinct lines. There are splittings which are coming from scalar coupling, which I will talk a bit later. The point is, even if you look at the same proton, depending upon the functional group, you get different spectral response, and that helps in assigning a complex molecule. So that is the advantage. The sensitivity of NMR spectroscopy is a function of the number of spins, the gyromagnetic ratio of the nucleus spins that you excite, what you detect, the magnetic field, the number of the scans in which you have to do the experiment, and there is something called the transverse relaxation time, which I will explain as we go on. There's a bit complicated function, but in a nutshell, if you actually work out the physics of it, the way it works is something like this. So you have the splitting of the two levels, the number of spins in the beta level with respect to the alpha level is given by the standard Boltzmann distribution, which is e to the power of minus delta E by kT. And if I take some standard values of the temperature magnetic field, the delta E will be something like this. The kT we know, so the delta E by kT is something like this. It's a very small number. In optical spectroscopy, this is a very large number. And that's the whole problem with NMR. The sensitivity is extremely poor, which means that this ratio n beta by n alpha, I can sort of do a series expansion of this exponential term, and that comes out to be delta E by 2 kT. So it is a difference in the population which gives rise to signal, because the sum is always 1. And the difference for these numbers is just 3.2 in the 10 to the minus 5. It's a factor of 2 here, which means if you have 1 million spin, there is only one spin there's only one population, just one population which is different in the upper level compared to the lower level. And that's an extremely lousy signal as far as NMR is concerned. So keep that in mind. So one has to come up with techniques to improve the quality of the signal, but the resolution is where you actually benefit. Now, having said that, those are some of the spectral response. If you look at the 1H NMR, the proton NMR, that's pretty good because proton has the highest abundance and the highest the gamma factor. But if you look at the carbon-13, it's the same number of scan. I mean, the signal to noise is not so good. And if you want to get the same kind of a response as the protons, the carbon-13 has to be accumulated for several hours. So that's the price you pay in terms of if you want to look at the carbon or the nitrogen-15 because of their low abundance and the low gyromagnetic ratio. But they're all useful for various purposes. So you can't just avoid these and just look at the protons. So that's not a feasible thing. The next thing you have to remember is that higher the magnetic field, higher is this population difference, and higher will be the sensitivity. That is one more reason to go into a higher and higher magnetic fields, although you pay a price in terms of real money, actually. I mean, the higher magnetic fields are much, much more expensive. So as you can see here, if you don't have a magnetic field, there is no population difference. If you have a magnetic field of about 2 Tesla, which corresponds to like 100 megahertz, there are 16 spins which are different. That's just nothing actually. Even if you go to something like 18.8 Tesla, which is like 800 megahertz, I mean, the difference in population is very, very less. It's just 128, which is a very small number. So, but you get 128 instead of 64. The signal intensity goes up by a factor of 2 in this case. So that's again a spectral example. So if you do the experiment on some sample at 30 megahertz, this is the quality of the spectrum that you get. But if you do it in a 500 megahertz, the quality improves, the sensitivity improves. The other thing which is important is the resolution and the dispersion increases. And how the dispersion increases is something which we will see in the later slides. So how does the chemical shift actually come about? The chemical shift is one of the most useful techniques for the structural characterization. And I can use that to distinguish the functional groups. So instead of getting just one line for this ethyl alcohol, you actually get 3 responses of the proton spectrum, which corresponds to your CH3 group, your CH2s, and the OH group. So that's the whole beauty of it. Now, where does this chemical shift come from? If you see 3 lines, that actually means that the 3 protons, the H3 over here, the H2, and the H, they have different Lambda frequencies. So where do they get different Lambda frequencies? It's not just one Lambda frequency across a sample. There are 3 different in this particular case. That's because the nuclear spins are not alone. So they have a rich electronic cloud. There are all kinds of electrons, the hybridized electrons which are moving around. And as you can very well imagine, the CH3, CH2, and the OH have different hybridizations and have different electronic density around it. And the moving electrons create another magnetic field. And that magnetic field can be either in the direction of the applied field or opposite. And that can actually create different Lambda frequencies for different protons in various functional groups. And that actually made NMR one of the most useful experiments. So the chemical shift is a very pivotal interaction in the spin system. And if you look at the energy level separation, so there are 3 different energy levels. So this one, which is coming at close to 0, will have the lowest of the separations and the highest of the separations, which we call the D-shielded one. So these are the D-shielded lines. These are the shielded ones, and they have different energy levels and different Lambda frequencies. So the chemical shift was actually sort of discovered by an Indian scientist at that time in the 50s, early 50s, and the late 40s in the Felix Bloch lab. So his name was Dharmati, Professor Dharmati, and he actually came back to TIFR and started the NMR group in TIFR. So this was one of the, he was also pivotal in establishing a huge workshop in NMR, and that was the inauguration of the facility, which was, of course, presided by Jawaharlal Nehru. And this was the founder of TIFR, Homi Bhabha. So that's a bit of a history over here. Right. So with all of these, NMR can actually look at various aspects of the matter. I mean, whether it is gaseous state, liquid state, or solid state, isotropic materials, anisotropic, ordered, disordered. Well, if you look at some of the X-rays, you need some well-defined crystals. You can do the powder NMR and the powder X-ray and so on and so forth. But NMR indeed covers a large range of materials, and not just the structural part, but also in terms of the dynamics. So you get this free induction decay is something which I said earlier on. The free induction decay has all the response, but it's very difficult to figure out what are the kind of frequencies. The major development which came in NMR was the Fourier transform. How does the Fourier transform work? So if you just think of somebody playing a piano or something like that, it's just fantastic. I mean, a very mellifluous music coming over, and you can appreciate it. But if you don't have the time to appreciate such good music, all you can do is to just break up the whole damn thing, right? You just break up the entire piano, all kind of notes will be produced. But I can do a mathematical analysis and get back the individual musical notes in a very precise way. I mean, this may not be the most romantic way of doing of listening to a music, but the music also you can actually create all the notes together and filter out in a Fourier transform, because the ear is a fantastic Fourier transform device. The other way in which people used to do NMR was to systematically scan the radio frequency field, and wherever it hits a resonance, you will get a signal, but that takes a long, long time. So that's not going to work for real samples. So you come up with a Fourier transform, So you collect all the signals in one go. That's what it says. So if you want to collect all the signals in one go, you cannot do a sweep NMR like this, but you have to come up with a pulse which has a sufficient bandwidth that will excite all the possible resonances in a given sample. And to decode it, you have to come up with a Fourier transform, and that is which is shown here, which was done by Richard Ernst way back in the mid 60s. And that sort of revolutionized NMR to more complicated molecules and biomolecules in particular. So that's a typical experiment. So the spins are aligned along the z-axis, the equilibrium magnetization, as we call it, the Boltzmann magnetization. And what we normally do is to come up with a radio frequency pulse. It's just a burst of an electromagnetic irradiation, sinusoidal. So the timing, I can adjust the timing of this, the duration, such that the magnetization flips by 90 degrees to the y-axis or the x-axis, which means I'm creating the maximal magnetization by a 90-degree pulse. So people talk about a 90-degree pulse, which just means that the equilibrium magnetization is tilted by 90 degrees. And then you switch off the RF, the magnetization will go back to the equilibrium, and that's the signal which you collect. All right. So I put a receiver along one of the axes, the x-axis or the y-axis. So once the created magnetization go back to equilibrium, the signal, which is the rotating signal, that induces a voltage in this particular coil. And that's the signal which I pick up as a time domain signal. So what I have shown here is a time domain signal that we pick up, which is Fourier transformed to give rise to a spectrum. So the spins, after you switch off the RF field, will actually persist in the XY plane, and the equilibrium magnetization is zero. It is along the z-axis. So one of the component will go back to the equilibrium value, and the other components, which are the XY component, will go back to zero because there is no equilibrium X and Y component. That's just transiently created one. So that's the process of NMR. So you get a response, and the signal actually dies down because of the relaxation, because the X and Y components have to go back to zero. And the time scale at which that goes back to zero is given by a constant, which is called a T2. And that is what we call as a transverse relaxation time. And you can Fourier transform this, and that gives rise to this kind of a spectrum. So that's what we get. So this is, again, another shot of this. So you have two kind of relaxation process which is happening here. So one is the spin relaxation, which is the X and Y component going to zero. That is this process. And then I have a longitudinal component going to zero, which is the MZ, which is going to M naught. So those are the two processes that is happening over here. And both the processes have physical significance, and we will see they go on. So that is the pulse, and the pulse has an amplitude, pulse has a phase, pulse has a frequency. And the frequency should match with the frequency of the spins that you're trying to see. Okay? And the spin relaxation, there are two major phenomena which gives rise to the relaxation. As we talked about a while ago, there is a longitudinal relaxation, which is the spins going back to the equilibrium value, which is M naught, and a transverse relaxation in which the X and Y components go to zero. Now, both of them have a physical meaning. The T1 relaxation is the one which determines the repetition rate of an experiment, because you have to do the signal averaging to collect the higher and higher quality signals. And the only way to do the T1 the only way to do the repetition is to wait for a certain period of time before you go back and pulse again. Because unless the spins have gone back to equilibrium, there is no point in coming with a pulse. So this period is defined by the spin relaxation. So the shorter the T1, the better it is. So you can pulse faster, the experiment can finish faster. And there are rigorous dependence of the T1 as a function of the tau C. So this is plotting the T1s and the T2. So that's the T1, and that's the T2 as a function of the size of the molecule. So when the molecular size becomes larger and larger, the T2 just goes down. And the T1 comes down and then goes up. And what is the significance of the T2 is in the line width. If you have a longer T2, like in this case, you have a sharper line. If you have a shorter T2, you have a broader line. So it is good to have a long T2, but in most of the biomolecules, you will have short T2s, and you will have a broader line width. So that is a fact of life anyway. The next question you can ask is, how can you measure these kind of time scales? The T1, as I stated, is a time scale with which the equilibrium magnetization go back to the Z component. So what you do is to create a non-equilibrium magnetization along the Z axis. I can't detect the Z, so immediately after I create this component, I come up with a 90-degree pulse, which will create an X magnetization or a Y magnetization. Now, if this delay is zero, practically zero, then the signal I get is the same as the equilibrium signal, except that the sign is inverted because I have inverted it with a 180-degree pulse here. And then I wait for some time, the signal goes back, and that going back is because of T1. And eventually, it will go back completely. So this tau is long enough, everything would have relaxed, and you get a maximum signal over here. Now, how does it help? So this is the profile of the signals that you get from this kind of an experiment, which is called an inversion recovery experiment. You invert, and then you recover during this period. And the intensity is plotted as this time constant tau, and that can be fitted into conventional block equations to get the T1. So I know the values of all these, and I can find out the T1s from this experiment. So that's a very useful experiment to find out what is the longitudinal relaxation time. So that's how the experiment works. If you plot the intensity profile, that's the graph you get. That's the minus of M naught, and then eventually it saturates. And this exponential fit gives me the T1 time constant. Now the T2, which is a transverse relaxation time, normally speaking is just the inverse of the line width. That is just the line width are related to relaxation. But that's not always true, for the simple reason that the sample that you have doesn't see the same magnetic field at all places. So you have a liquid sample in an NMR sample holder. Some of you might have done the experiment. So then there's a glass capillary tube in which the sample is kept. So the green are the sample spins or the sample species. Now we believe, or we are told, that there is one magnetic field, which is B naught. Now that's not completely true, because the magnetic fields can never be homogeneous. So this sample actually sees different magnetic fields in different positions. So even this much difference in the length can actually force the sample to see different magnetic fields, and that is what we call as an inhomogeneous broadening. And because of the inhomogeneous broadening, this part of the some part of the sample will have a sharp line at a particular resonance, and the other ones will have a sharp line at another resonance. So that is two different profiles. And what you see is a cumulative response, which is not your original 1/T2. So that is a different T2s. So the T2 you measure from the line width is not the real one. That will be even shorter, actually. So the question you can ask yourself is, how can you get rid of this inhomogeneous effect? How can you tell the spins that your magnetic field is not drifting or something like that, and measure the T2s? So you have to measure the T2, you have to get the full free induction decay without any of these issues. So how can you do that? And that is something which people figured out already in the 50s by spin echo schemes. And okay, so this is another experiment to show that even if you have a well shimmed, which means the field is believed to be homogeneous, the actual T2 is given over here, 19 seconds or so. But the T2, if you measure it from your line width, it will be terribly slower. So don't believe the line width kind of measurement. You have to do the spin echo experiment. And how do you do spin echo? I mean, I can just hear lots of people talking in the background. Yeah. All right. So that's the experiment which one has to do, which gives rise to the T2s. And normally, the T1s are longer than the T2s. And in solution, at least, in liquid samples, the T1 is equal to T2s. Now, there's an interesting paper which some of you might want to look it up, whether T2 can be longer than T1. So this is a paper which really talks about the physics of these relaxation time scales by Traficante way back in the 90s. Anyway, so come back to the point, how do you measure the T2s and how do you remove the inhomogeneities? So the spins are subjected to certain inhomogeneous effects, some issues, and we have to make the spins pretend that those effects are not there. So what you can think of is as this cover picture says, so this is an article from 1953 by Erwin Hahn, who actually did the spinnaker for the first time. So the way he thought about it was there's a bunch of people running. So maybe you guys are running and I'm also running over here. So you start the running 400-meter race or something like that. And of course, I run very, very slow. So I'm somewhere over here. All the students are running very fast. There's a big separation over here. So now you can see there's a big separation. So I'm somewhere here. But now what happens is that at this particular point of time, you know, the referee just decides that, you know, he's actually going to ask everyone to run backwards. So far, everyone was running forward, and now everyone is running backwards at a particular instant of time, which is like half of the time. And then, if you wait for half more time, what will be the result? The result will be just that, you know, everyone would have reached the same time point or the same.
Excuse me, sir. Excuse me, sir. The slides are not full screen now. Somebody interrupted, I think.
Yeah, I mean, somebody was sharing the screen. Okay.
Yeah.
Go back.
I have a request to the participants. Please don't share or switch on your mic during the presentation.
Right, that should be okay.
Yeah,
right?
thank you. Yeah, it's fine. Thank you. Sorry for this.
Right.
Yeah.
Does it change? No. Okay, just hold on for a second. Sorry.
Yeah.
This is okay. I think I have. Sorry. Right, just hold on. I'm just trying.
Yeah.
Right, no, I'm just unable to get it back actually. Can I just log out and come in? Is that
Yeah, please. Yeah. So, dear audience, please don't switch on your mic or share anything during the talk.
Professor Madhu, it seems you have muted. We can't hear you anything.
Right.
Yeah, right. It's okay now.
I can't get to the full screen for some reason. Yeah. But let me just continue this way. Otherwise, we're just wasting time.
Yeah.
This, you can see the screen, I believe.
Yeah,
Right.
we can see this. Yes. Yeah.
Right, right. So that's the whole idea of the spinnaker. So you start at some point of time where everyone looks the same, and then you keep running around. There is a distinct separation which is building up. But then if you turn back and run, then there is no difference actually. So that's a good thing. What it actually says is that nothing has happened. So whatever happened over here is actually traced back. And that is what which we call it as echoing a particular phenomenon or refocusing. I think there are audience with the microphone on. Yeah, thanks. And that is an experiment which is very important because the spins actually now behave as if it has not felt any of those inhomogeneous effects. Now, how do you do that in terms of the radio frequency pulses, not by whistling or something like that? That's rather easy, actually. So you start with the nucleus spins, you put a 90-degree pulse, and they start running. And the running is over here. And different spins will run in different ways because they have different Lambda frequencies. So they dephase in different ways. But now a turnaround. So that's when the whistle starts and people start running backwards, which is a 180-degree pulse. And they actually go in the opposite direction. So it's a 180-degree flip. Now, once you do a 180-degree flip, whatever which moved in this direction now will move in the opposite direction. So you can see that at this point of time, and at this point of time, which is over here and which is over here, there is absolutely no change as far as the signal is concerned. The sense has changed. It is positive, it is negative here, but the magnitude is the same. And that's the good thing of the spinnaker experiment. So you can refocus all the inhomogeneity, all the effects of the magnetic field and everything get refocused, and you get a sharp signal, the inverse of which will actually give you the line width. And that is what we have done here. So you do the experiment, you keep collecting the signal as a function of the tau, and that can be fitted into a simple exponential to get the transverse relaxation time. Right. You can do the experiment in different ways. You can actually repeat this particular block, or you can actually increment the tau duration over here. They have certain disadvantages and advantages, but you can quantitatively pick up the T2 measurements. And this is something which people also call it as a Carr-Purcell Myboom-Gill sequence, but that's more of a technical name. We don't have to quite worry about it. So as you can see that this T2 relaxation has a fundamental connection to the line width and also to the size of the molecule, which manifests in terms of the correlation times. And it's a good indicator to also figure out what is the size of the molecule once you have an idea about the transverse relaxation. More important is the fact that the T1s and the T2s are good parameters or good indicators of the mobility in a given molecular system, the flexible chains having a narrower line width than a globular protein, and so on and so forth. So these are all, a quick way to estimate what is the kind of dynamics which is present in a spin system. So the T1 relaxation, the way it relaxes, different resonances in a given sample also will have different T1s. And that also tells you something about the mobility or the rigidity across the resonances in a given system. So that's a summary of what I have talked so far before we get into a little bit more involved issues. So the intensity is given by the first point of the free induction decay, and the resolution is given by how long the free induction decay goes on, which is your transverse relaxation time. All right, so that's a typical spectrum of the big molecules. So this is a molecule, a protein of lysozyme, and you can see that there's a fair amount of resolution all over. And tomorrow in a lecture, we will see that this is not good enough. We have to do higher dimensional spectroscopy to even improve the quality of this kind of a spectrum. But it can be done, and there have been many advantages, some of which we have seen earlier on. The Fourier transform came in the mid-60s. The two-dimensional spectroscopy came in the 70s. And people who pioneered this are Richard Ernst, Paul Lautenbauer, Peter Mansfield, and so on and so forth. And technology-wise, also there have been many advances. We started with electromagnets, and now we have magnetic fields, which go up to 1.1, 1.2 gigahertz. And that's like a 28 to 30 Tesla of the superconducting magnets. The whole magnet industry has evolved quite fantastically in terms of coming up with coils which have a good perseverance and which can carry electric currents to sustain such very high superconducting magnetic fields also. And all these have enabled NMR to get into, higher and higher proteins. So starting from very small molecules, we have gone up to 100 kilodaltons and even more. Some data which I will show you as we go on. So that's in the application front of nuclear magnetic resonance. So just a couple of slides to show that India is pretty much well into the NMR research. There are plenty of labs doing nuclear magnetic resonance research and applications. The list is by no means exclusive. There are much more than what I have listed over here. Many of the CSIR labs, IITs, ISARs, and all kinds of such places. A snapshot of the research that we do in many cases is the improving the technique itself, which is improving the sensitivity and resolution of the Nmr spectroscopy. The hardware development, which we do quite a bit, the theory of the nuclear spins, quantum computation, the optical spectroscopy, combining it with the NMR is some other thing which we do with. And the applications, of course, span materials to biology, to metabolomics, to imaging. So materials, one can look at all these classes of molecules, samples. Biology, again, some of which Chari must have mentioned in the mornings, the structures and the dynamics of a class of biomolecules. Metabolic profiling is another important thing. And imaging, of course. And all these, if you look at the PDB, which is a protein database, you can, of course, X-ray leads much better than any other technique. But NMR has its niche areas of looking at a specific class of all these molecular systems. And these are the number of structures that are in the PDB, which have been obtained with nuclear magnetic resonance. So how have these been possible? So that is something which we will see in the next half an hour or so. So the information contained in NMR spectrum, they observe the following. So there's a peak position, which comes from the chemical shift, which is quantitative. That tells you about the chemical environment. There's a peak splitting, which comes from the scalar coupling constant. That tells me about the number of neighboring nuclei, the torsion angles, and so on and so forth. The intensity tells me about the number of nuclei that contribute to that particular signal, and that's the integral. And the peak shape tells me about the transverse relaxation time, or the molecular motion, or the chemical exchange. So each one of these attributes of a nuclear signal has a meaning. The chemical shift, as I said, is the magnetic field which is induced by the electronic cloud, which goes against or for the magnetic field. And that is how you see different resonances for the same protons in a given sample. So depending upon the electronic cloud, the CH3, CH2, and many other guys will have different magnetic field. So the field that a particular spin sees is not just B naught, it is B naught, which is modulated by the chemical shift, which depends on the electronic cloud. So that's something which one has to keep in mind. And this is extremely useful for assignments. This is an example of another chemical shift spectrum of phenylaceton. Each type of proton will come at different places. Of course, these are referenced with respect to something called tetramethylsilane. And the reason for taking the tetramethylsilane is because they come at very far away from the protons of interest, and it doesn't interfere with the other, the samples actually. Now, there's something the funny thing which the NMR people do is that they don't report the resonances in hertz. They report the resonances in parts per million. So the question obviously is, why do the NMR people go for such a dimensionless unit rather than talking in terms of the hertz, which is what optical spectroscopy and the other people do it. So the 1 ppm, which is parts per million, so 1 ppm for proton spectroscopy, which is 500 megahertz, let's say that's the machine, 1 ppm will correspond to 500 hertz. It's 10 to the minus 6 multiplication factor. If it is 600 megahertz, the proton spectrum, 1 ppm is 600 hertz. The same thing, if you look at the carbon-13, the 1 ppm will be 1/4, because the aromatic ratio is 1/4. The nitrogen will be 1/10 actually. So those are the numbers which you have to keep in mind. And the chemical shift, the unit is delta, which is ppm, which is a dimensionless number. Real shift in hertz divided by the spectrometer frequency. Now, the good thing of this unit is dimensionless. So whichever spectrometer you use, if one line comes at 1.2 ppm, it will be always at 1.2 ppm, irrespective of the machine that you use or the magnetic field. But you have to multiply it with the corresponding spectrometer frequency to convert that into the frequency unit. That's something which one has to keep in mind. So these are some of the chemical shift scales which you can find in standard chemistry textbooks. The spread in the protons of about 10 to 15 ppm. For carbons, it is typically of the order of 200 to 270 ppm. For the nitrogen, you get a spread of about 160 ppm. But as you can see, the most important thing is the functional groups have a unique signature, have a unique position where they resonate. And this is, again, another way to look at it is right from the aliphatic to the carbonyls, the protons come in various ppm positions, and you can assign your compound given this kind of information already. And there are many other factors which determine the resonance positions, and not just the absolute chemical shift, which can be modulated by surrounding electronegative elements, the pi bonds, or the hydrogen bonding. So like if you have the electronegative elements like the chlorine, the higher it is or the number of it is, it de-shields the proton, which means the lines will come towards the left side of the TMS peaks. If the chlorine were not there, the H will come somewhere here. As the electronegativity increases or the number increases of the atoms, the lines will go further and further to the left side. And that's what I have shown over here. For a particular compound CH3X, depending upon the element X, its electronegativity, the chemical shift actually has a nice variation. So the more electronegative, the more de-shielded the nuclear spin that you're looking at is. And similarly, the number is if you have more of such electronegative elements, again, the more shielded it becomes. So the effect increases with increasing numbers and decreases with the increasing distance, as in this case. You can also have the aromatic ring current effect. The classic case is perhaps of the benzene ring. And there, actually, the ring protons can get extremely de-shielded, unlike in the case of a cyclohexane, because all these electrons actually produce more and more magnetic fields, and they can add more to the chemical shift. So that's precisely what it happens. Again, that's an influence of the hydrogen bonding. So if you have strong hydrogen bondings, again, the nuclear spins will get de-shielded, which is another indicator to find out whether you have hydrogen bond or not. So the OH itself can come in various positions. So the OH absorption could be 4.2 ppm, but it could be as high as 10 to 12 ppm in some cases. That is another example. So the alcohols can vary in chemical shift from 0.5, as I said, which is without the hydrogen bonding. And if you have lots of hydrogen bonding, like in this case, the line can actually get shifted almost a factor of 10, in fact. So that's the influence of the hydrogen bond and a good indicator. So this is the hydrogen bonds. Without the hydrogen bonding, the line's coming closer to zero. Well, if you have the hydrogen bond, they actually get shifted. So that's about the position. And what can you talk about the splitting? So we saw some spectra in which the CH3 was split. And this is coming from the through bond coupling, which is what we call as a scalar coupling. And that's a multiplet pattern. The standard rule which people learn in chemistry is that if you have a proton coupled to n other proton, you get a splitting by n plus 1. We will see in a naive way, where does this n plus 1 come from? So the scalar coupling is mediated through, again, the surrounding electron. It is through the bond. So the one bond or two bond or three bond. So the nuclear spins are over here, and the electronic spins are the ones which couple them. So it's an indirect interaction, it's a magnetic field, and it has valuable information about the dihedral bond angles, hybridization, and things like that. So that's how the two bond couplings behave as a function of one of the torsional angles. And if you can measure it, I can already say something about the torsional angles in such molecules. And this is something which I can fit into the Karplus relation, which is given over here. And that Karplus relation can be identified with the positioning of that particular angle in the Ramachandran plot. And I already get a preliminary information about the secondary structure of a biomolecule from a simple measurement of the scalar couplings. So that's an extremely powerful interaction. Now, how does it work? So before we get into that, we have to identify the spin system. It's again an NMR spectroscopist way of looking at the spins. So there are two kind of equivalences which one can think of. A chemical equivalence, like this molecule, where the spins, like the protons here or the fluorines, are the same isotopic species, and there is a molecular symmetry which can exchange the two spins. I can have a magnetic equivalence, which is much stronger, which means that there is all the spins should have the same chemical shift. Like in this case, the HAB have the same chemical shift, so they are magnetically equivalent. H1, H2, H3, they are magnetic equivalent, which means the spin should have the same couplings to all the other spins, or you should not have any couplings. The chemical equivalence and magnetic equivalence, this is much stronger. So when you have, so how do you sort of put the spins in a nomenclature? If you don't have the magnetic equivalent, the chemical equivalent, so these two are chemical equivalent, these two are chemical equivalent, I call it as an A prime, X prime system. If I have a magnetic equivalent, so I call these H1, H2, H3 as X3, and HA and HP are A2. So this is an A2 X3 system. Now it is called an A and X because they are far away in the bond. That's the only reason. If they are closer in the bond, then you have to call it as an AB kind of a spin system. So that's the kind of nomenclature that we adopt. So this is an example of an A prime, X prime spin system, CH2F2 or something like this. And it has all its unique spectral signatures with the split patterns. And I will come to that in a minute. So where does the N+1 rule come from? So I have a CH here coupled to a CH2 through bond coupling. And this H, if you take the resonance of this H, it's not one line, it actually gives me three lines, a triplet, because it is coupled to two proton. If I take the spectrum of the CH2, the two proton coupled to one here, that gives me a doublet because it is coupled to just one. Now, if you get more lines than one, that means that there are more energy levels. So where are these energy levels coming from? That's something which is interesting. Now, protons which are equivalent by symmetry, they don't split. So in this case, there is no splitting. And there is no splitting over here if X is also equal to Y. And protons in the same group also do not split. Within CH3, there is no split. Within CH2, there is no split. But otherwise, it splits. So if I have a CH and X is not equal to Y, then you get a doublet for each proton. CH3CH, the H3 will become a doublet because of the H. H will become a quartet because it is coupled to three protons, so the N+1 is 4. CH2CH will give me a doublet, triplet. 3, 2 will give me a triplet, quartet. And the CH3CH3CH, this gives me a heptet, 7 lines here, because this H is coupled to 6 protons, that gives me 7 lines. So all kind of funny patterns exist, and all of them can be theoretically predicted and calculated as well. So the measured scalar coupling is the separation between these two lines. So that's the important parameter here. So the coupling constant, as the name says, it is a constant, and the coupling constant is the separation between the split pattern. That's the scalar coupling constant, the bond strength. It's an interaction, the strength of the interaction between the two sets of hydrogen creating the multiplet. And there are many orders of these magnitudes, something like the proton-proton couplings are generally weak. The proton-carbon couplings can be 100 hertz to 150 hertz. Similarly for the proton-nitrogens and so on and so forth. All of them can be measured quite well with NMR. Now, what is the origin of the splitting, at least in a naive way? Because if more lines are coming here compared to here, there should be more energy levels. There should be more transitions. So one way to look at it is from a simple Pauli exclusion principle. So I have a fluorine spectrum being looked at. It has its electronic spins, which are these red guys. Now, because of the Pauli exclusion principle, the electronic spin over here should be down if it is up if it is down, which means the proton spin on this side will have a slightly different energy compared to this proton because electronic configuration is different. And that slight difference in energy is good enough to give a splitting or additional energy levels. And you can also go through the entire CH2 system. All you have to do is to keep marking the proton spins and the corresponding electron spins. And you can see that they keep changing. And the number of such changes will correspond to the N+1 rule. And in an energy level representation, this is how it looks like. So you have 2 energy levels in the normal case, and it will become 4 energy levels when I have a partner spin coming up over here. And that is where I get the doublet or the triplet, etc. Another way to look at this, if I look at the energy levels of CH2, CH2 has 4 energy levels because it is 2 spins. 2 spins have 4 energy levels. 3 spins have 8 energy levels. The proton that you take here, it sees 4 equivalent configuration here. And that's the origin of the quartet. If you take any proton here, it sees 4. And that is, it sees 3. That's the origin of the triplet. So you can also quantify the numbers in the split pattern by just looking at the energy levels. Of course, you can work out the mathematics and do it in a better way. And that is what we call it as a first order splitting or the first order spectrum, where I can get the normal splittings and the separation giving rise to the scalar coupling. Now, the split pattern goes like this. If I have 1 spin, there is, of course, no split. If it is coupled to 2, I get this. If it is coupled to 1 more, I get a doublet. If it is coupled to 1 more, I get a triplet, and so on and so forth. It turns out that these intensities go by the binomial expansion coefficients, and it forms a triangle like this, the numbers in the triplet or the quartet. So the triplet, the central one, so if I take a triplet, it is like a 1:2:1 ratio, and that is the CH2 triplet. If I take a quartet, it is 1:3:3:1 in terms of intensity. The central 2 lines will be much higher than the outer lines, and so on and so forth. And that's a Pascal's triangle, and one can calculate all this stuff and get the maximal information. So that's a real example of one of the split pattern of nitropropane. You get all the splittings. We can calculate the coupling constant and the torsional parameters. So this is how the mathematics goes. I won't go into the detail. You can work out the energy levels, the eigenvalues. You can calculate the frequencies and the energy separations as well, and the intensities. And this is how the intensities go. If I have a completely coupled spin system, A2, you just get 1 line where every line collapses. And if I have an AX spin system, weakly coupled, which means that the chemical shift difference is much larger than the scalar couplings, you get a well-resolved a doublet of a doublet and a doublet for the 2 spins. This is another example where the transitions can happen from A2X to A2B. And the typical molecule which show an AB kind of a pattern. And the spectrum can get complicated as we have more and more kind of a spins. This is an AA prime, XS prime, 4-spin system. You get all kinds of splittings over here. Now, the splittings are interesting in the sense that that also gives me a way to convince you that the high magnetic field is indeed useful. So we already saw that it is useful in terms of the sensitivity. But now let's look at the spectrum at 100 megahertz and 200 megahertz of an arbitrary pattern. So here I have a triplet and a quartet. The triplet has 7.5 hertz separation. The quartet also has 7.5. If I plot the spectrum in 200 megahertz with half the ppms, it's not the 6 ppm. In 3 ppm, it looks like this. So the frequency is the same because it's a scalar coupling constant. It's a constant. But now if I keep the ppm scale the same, which is what one should do, so the hertz will actually get compressed. Because I go from here to here, the hertz get compressed, so that's how it comes about. But the interesting thing is this separation increases quite a lot. And that is what we call as the dispersion of the spectral line. So you can actually find out which is the multiplet belonging to which the main line. Now, that is even more clearer here. So you have 3 resonances split in the scalar pattern. And I can't even figure out whether this is actually of the green line or this is of the brown one. There is no way to distinguish because everything is overlapping. But now when I increase the field, it gets slightly better, but not very much. And when I go to 200 megahertz, each pattern comes out uniquely well-defined. So that's the advantage of going to the higher and higher magnetic fields. And this becomes even better at very high magnetic field, which is what we call as the dispersion in the given spectrometer. Besides this, the major thing, as I said earlier on, is the fact that you can look at the dynamics, which is a whole bunch of dynamics that we can look at. There's a various time scales, and all of them can be probed with NMR. There is a particular experiment that one can identify for a given dynamics. So that's the beauty of nuclear magnetic resonance, and at least in my personal opinion, This is a niche area of NMR. So here, I mean, I won't go into the details of this because we haven't yet looked at the two-dimensional NMR. So this is a little bit advanced technique, but I just want to tell you that you suggest a problem of you want to look at fluctuations or group motions or rotations. For any particular thing, there is a given NMR experiment to do that. And that gives the time scale pretty well. So these are again, just to highlight the fact that you can have very fast time scales in a given molecule to slow, and each one of them come under a specific chemical property like the vibrations, rotations, chemical exchange, diffusion, and I can characterize it with nuclear magnetic resonance. So here is an example of a chemical exchange in a methyl formamide, for instance. And depending upon the exchange time scale, I get different kind of spectra. If the exchange is slow in the NMR time scale, you get sharp lines. If the exchange is fast enough, I get broad lines. And they can be fitted, and I can use it to calculate the free energy parameters. So the slow exchange, I get both the fast exchange, I get just one of the lines. The slow exchange, I can differentiate between these two protons, and I get two lines, and at some point they interfere and collapse. And this is a clear indicator to the thermodynamic processes in a given sample as well. This is another example from a paper published in '84 of the exchange rate induced line broadening or line narrowing. It has a large potential for understanding. Now, integration is another thing which actually tells me the area under the peak, and that is a factor which gives me the number of hydrogens or the number of the carbons in a given sample. So this is an example of a benzyl acetate. I find out the area under the curve, and area under the curve is the integral, and normalize it to something which you know. And once you know the known samples integral, the known resonance integral, I can find out the overall number of protons or carbons from a given spectrum. So this is another example over here. I can do the integrals and pretty much get a ballpark estimate of it. It's not highly accurate because there is an issue with a uniform excitation, but it gives you a ballpark estimate. So the summary is this so far. I mean, so every type of hydrogen gives a unique peak. The chemical shift tells me the type of hydrogen. The integral gives me the number of such hydrogen. The spin splitting gives a number of hydrogens of the adjacent carbons, and the coupling constant gives me ideas about the dihedral angles and things like that. So before I wrap up, let me just briefly tell you about the carbon NMR and some other nuclei. So carbon-12 is the abundant one, but that's not NMR active. The spin is 0, while the 13C is spin half. And the problem is it is 1.1% abundant only. So normally the biomolecules, people would love to enrich the compound by, you know, the 13C enrichment and so on and so forth to make the abundance close to 100%. So the signals are very weak because of this and because of the low gyromagnetic ratio. So for a given field strength, the carbon-13 has a resonance which is 1/4 affected. So protons at 11 Tesla has 500 megahertz. Carbon will be 125. At 800 megahertz, carbon will be 200. So that's the gyromagnetic ratio factor in which the hydrogen frequency gets divided by a factor of 4 for 13C. For N15, it's a factor of 10. Now, because of the low abundance of the carbon-carbon coupling is practically invisible unless you enrich it. I mean, you can see that in a good system, of course. The carbon-proton couplings are the ones which people exploit quite a lot. These are of the order of 100 hertz, 150 hertz of that kind. And they also give similar kind of splitting as we saw in the case of the proton-proton. So 3 protons and carbon, if I look at the carbon, it actually gives me a quartet. Here it gives me a triplet for methylene. For methine, it gives me a doublet. For quaternary, there is nothing. And the effect is the same. It's n+1. The mathematics is also the same. The constants are much higher. It's 100 to 200 hertz. So this is another spectrum of ethyl phenyl acetate with the couplings. Now, you have to realize one thing, whether you need the coupling to be present in a spectrum or not. The chemical shift is the first important thing in a spectrum, which tells me the assignment. Now, coupling in many cases are actually not so good because they complicate the spectrum because you get a large number of multiplied patterns and you don't want to spend your time to analyze which is which. So it is good in some cases to remove the coupling, but the couplings cannot be just removed. I mean, these are inherent. So you have to come up with some clever NMR ways, and I will just show one slide at the end as to how to remove these scalar couplings and simplify the spectrum. So that is what we do. It is so what we have here is carbon-13, which is coupled to the proton. So all the couplings are there. And you can see that there is no spectrum at all. And that's because you have a large number of splittings and everything just broadens out. But now I remove the couplings. I mean, don't ask me how we do that. I will show you a slide later. And then all the individual carbons come up. And that's the beauty of it. So you remove the couplings through some means, and then I can get the high resolution carbon-13 spectrum, which I can use to get the chemical shift and the assignment. And then I can go back and look at the couplings in a two-dimensional way or something like that, which also we will see maybe tomorrow. So how do you do this decoupling? So this is something which we call it as an heteronuclear spin decoupling in solution NMR. So the way one does it is rather simple. So you have the carbon chemical shift, which is written over here. These are the red one, that's my carbon spins, that is coupled to the different protons or the different hydrogens, which are coupled by this scalar couplings, which are these red arrows. And what I'm trying to do is to come up with some kind of a radio frequency radiation, which breaks the bond somehow or the other, which removes the bond. And then I can look at the carbons as if there is no scalar coupling to the adjacent proton. So that's the whole thing which we're doing. You know, it's a bit more difficult than saying in the simple words, but one can do it. So I excite the carbons and I come up with a continuous wave irradiation on the protons. I mean, if you don't want to think too much about it, it's just saturating the protons in some clever way so that the coupled carbons don't see the effect of it. So you can do that. So if you take an AX spin system, you get a doublet for the A or for the X. Now let's imagine that this is a carbon proton. So I'm looking at the proton spins coupled to the carbons. I'm looking at the carbons and I'm irradiating the protons. And what it essentially does is to collapse these two lines into one line. It removes the scalar couplings by this clever RF irradiation. It simplifies the spectrum. And that's a good way to get rid of the scalar couplings, the multiplied patterns, and I can look at the chemical shifts only. So that's the advantage of such kind of decoupling, which is very routinely used in NMR, whether it is solution state or solid state. The CW technique that I highlighted is one of the easiest ones, simple to think, but that's not probably the most efficient. There are more complicated pulse schemes which have been developed over the years. So these are some of the research topics which people still work on to improve the quality of the spectrum in terms of sensitivity and resolution. So these are called a double resonance technique because you pulse on one of the nucleus, you observe again by pulsing on another nucleus, and there are many such double resonance techniques, some of which we will see tomorrow as well. So I'm more or less towards the end of my presentation. So these are some of the books which you might want to look at to get a good idea of what I have taught so far. I can also share my slides to anyone. I can send it to Sunil and he can just distribute it as well. So a very useful book from the chemistry point of view, talking about the splittings, etc., is the Robert Harris. This is a very strongly recommended one. Andrew Jerome is another one which puts these concepts in a very pedagogical way. The NMR toolkit is a good one to look at some specific examples. If you are more adventurous and if you want to understand the quantum mechanics and the spin physics of nuclear resonance, including the design and where the research stands, there's a very excellent book and very elegant one written by Martin for the spin dynamics. So that's another strongly recommended one if you want to know the quantifiable parameters. Right. So that's, again, another example in which the decoupling helps the simplification. So this is with the scalar coupling. And then if you remove the scalar coupling, the triplet collapses into a singlet. This triplet collapses into a singlet, so on and so forth. So I know exactly which functional group. And then I can go back to the spectrum to calculate the scalar coupling. So you have to pay a price. You may have to do multiple experiments, but the information content that you get is much larger. Again, just like in the case of the hydrogen, the protons, the carbon-13 also has a chemical shift chart, well standardized. Many of the functional groups, we know where they actually come in. So that gives a good indicator of the resonance assignment. This is another way of putting this chart, the nitriles, the amides, esters, all of them will come in different positions, but just note that the chemical shift dispersion is much more for the carbons, like 270 ppm of that order, compared to the hydrogens, which is just about 10 to 20 ppm. So that in terms of dispersion, probably it is good to go to carbon. In terms of sensitivity, that's not a good idea. So again, one can do the structure determination. So I won't go into the details today. I think some other people might be covering it. But the parameters that you need for the structure determination or for the dynamics is the chemical shift, the scalar coupling, and there are lots of experiments which one can do to get that. I will just touch upon just briefly right now on something called INEPT, which is called the insensitive nuclei, the polarization transfer. Well, I think I will do that tomorrow, not today, actually. I mean, one thing you can do is, there's something called a so in the previous slide, we actually took two different classes of nuclear spins and decoupled one of them. I can also come up with the selective pulses on the coupled same kind of nuclear spins. And this way I can do a spectral editing. So I irradiate this particular spin. So this is a normal spectrum of a molecule. If I irradiate this particular spin, this multiplet is unaffected. This collapses, which means these two hydrogens are coupled to each other. Now I irradiate this one, the same thing happens. This is not affected, while this multiplet disappears, which means these two guys are coupled with a sizable scalar coupling, while this is far away. So this is a good way to know that which is coupled and which is not coupled. Of course, this takes a long time, and the best way to do in a two-dimensional way, which is what we will see tomorrow. I can also do a temperature variation, and that is useful to delineate or find out the hydrogen bonds in the peptides. As we saw earlier on, the hydrogen bonds have a good dispersion in terms of where the resonances come, deshielded or shielded. And the temperature studies can also tell me about the chemical exchange or the conformational equilibrium as well, which is something which people use quite a lot. So this is the temperature variation, which is shown for a peptide molecule. You can see that there are resonances like this, which keep on shifting. The multiplet structure also keep on changing. And that tells me something about that local environment of the molecule, which undergoes some kind of a conformational degree of freedom. So these are initial things which one should do to get an idea of the molecule that you will be having. And then you can build upon that with more sophisticated experiments. Right, so I sort of conclude here. So this is an exercise in which I think we dealt with the principles of NMR as to how to get a basic spectrum, the parameters like chemical shift, scalar coupling, the T1s, T2s, the peak integrals, and how they can be used to sort of get qualitative information about the molecule in hand, and in some cases quantitative as well. And we believe that NMR is still an evolving technique with more and more of these pulse sequences coming up, and a versatile tool with lots of implications and applications in a whole range of science disciplines. Good, so I'll stop here, and thanks for listening. I'm sorry that there was some interruptions in between, and if beyond my control, sorry about that. Right.
Thank you very much for the very informative talk. Sir, can you hear me?
Hello.
Hello?
Hello, yeah, please.
Can you hear me?
Yes, I can hear you, yeah.
Yeah, thank you very much for the very informative talk. Now this is the time for discussion. If someone has some question, you please ask. Or you can post your questions in the chat box.
You can type.
That's also possible
as well. Yeah, please.
Yeah. Hello? Audience? Any questions from your side? I think there are no questions.
Right.
Yeah. So thank you very much again
Sure.
for your very, very informative talk.
So we meet up at 2 o'clock tomorrow as well, right?
Yeah.
Tomorrow.
Yeah.
Tomorrow morning section starts at 9:30.
Okay.
So that is Dr. Vinesh Rajan from ISA Trivandrum, and your talk will be 2 o'clock tomorrow.
All right.
I will send you the link tonight.
Sure.
Okay, thank you. Thank you for the presentation.
Yeah.
I think the
Thank you very much.
students understood everything or didn't understand anything.